Here we're given a diagram of an asteroid with equations x equals a cosine cubed of theta, y equals a sine cubed of theta. We see that its maximum distance from the origin is a. That's because when the cosine and sine have their maximum, x and y become a, right? But let's just go ahead and articulate some things here. We have the point a0 on the x-axis. Now that associates with when the cosine is at a maximum and the sine is 0, and so when theta is equal to 0. We have the point 0a when the cosine function evaluates to 0 and the sine function evaluates to 1. So that would be when theta is equal to pi over 2. We'll set that aside for the time being, but it's there. Recall that area is given by the integral from a to b of y dx. It's really important to note that here a and b are x limits. We're going to set up our integral in theta, so we need to consider theta limits. Now we'll set that aside for the moment and work with the equations that we have. Y is equal to a times the sine cubed of theta. And since x is equal to a times the cosine cubed of theta, dx, we'll use the chain rule, and we get negative 3a cosine squared of theta sine of theta d theta, of course the negative coming about because the derivative of the cosine function is the negative sine. Using our expressions for y and dx, we get that the area is an integral, we'll deal with the limits in just a minute, of a sine cubed of theta for y times negative 3a cosine squared of theta sine of theta d theta for dx. Now let's go back to this idea of the fact that we had x limits and we are now going to need theta limits. X in our diagram goes from negative a to a, but we can take advantage of some symmetry. So we're actually just going to use what we see in the first quadrant and quadruple it. So back to our integral, we're going to write 4 in front of the whole thing. Now, in that first quadrant, x goes from 0 to a. When x is 0, that associates with theta equaling pi over 2. When x is a, that associates when theta equals 0. So our limits of integration are going to be pi over 2 to 0, which feels like they're upside down. But we also have a minus sign inside of our integrand, and so we can rewrite this whole thing as a equals 12, because we're going to multiply 3 by 4, times the integral from 0 to pi over 2, incorporating that negative by reversing the limits of integration. A squared, I guess I could have pulled that out front, but I didn't. Sine cubed times sine is going to give me sine to the 4th of theta, and then we have a cosine squared of theta d theta. Now this is a pretty bad integral here. We could use power reducing formulas and we'd end up with something horrific. At this point, I'll remind you that we have tables that give us ways to compute integrals like this. And what I see here is one form that looks like the integral of the sine to the n of u times the cosine to the m of u du. And in fact, there are two different representations that we can use. Remember that we had sine to the 4th of theta and cosine squared of theta. So I'm looking here at the first form where the result is negative sine to the n minus 1 of u cosine to the m plus 1 of u divided by n plus m plus n minus 1 over n plus m times the integral of sine to the n minus 2 of u cosine to the m of u du. What I'm noticing here is that the sine to the n minus 2 of u means that that sine power is going to drop. And so I'm going to use this form here. And you can verify that the result will become that a is equal to 12 lowercase a squared times negative sine cubed of theta cosine cubed of theta divided by 6, that'll go from 0 to pi over 2, plus 3 over 6, that would reduce, but that's what we get directly, times the integral from 0 to pi over 2 of the sine squared of theta cosine squared of theta d theta. Now the first term that we just wrote is going to become 0 when theta is either 0 or 2 pi, because we have a factor of sine of theta and we have a factor of cosine of theta. The 12a squared was in front of the whole thing, and so at this point what we now have is 6a squared times the integral from 0 to pi over 2 of the sine squared of theta times the cosine squared of theta d theta. Now we could use that form again, or as it turns out, the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. And so if I divide both sides by 2 and then square them, I get that the sine squared of 2 theta over 4 can replace the sine squared of theta times the cosine squared of theta. So the area then becomes 3 over 2a squared, because we have 6 divided by 4, times the integral from 0 to pi over 2 of the sine squared of 2 theta d theta. Using a power reducing formula, we get that a is equal to 3/4 times lowercase a squared times the integral from 0 to pi over 2 of 1 minus the cosine of 4 theta d theta. So we get 3/4 a squared times the quantity of theta minus 1/4 times the sine of 4 theta evaluated from 0 to pi over 2. And we again have the case where putting either 0 or pi over 2 in place of theta for the sine function is going to give us 0. Finally, then we can say that our area is equal to 3 pi a squared over 8. The point I wanted to make with this exercise was not really the trig stuff, although that's going to show up here and there. And it wasn't really using the table that's going to show up here and there as well. It was really the idea that we had to interpret our limits as starting out as x limits and then thinking how they would convert into theta limits. And then the idea that y dx comes directly from the equations that we were given. Now, if you'll bear with me for just a little bit longer here. What about x equals a cosine theta, y equals a sine theta, theta going from 0 to 2 pi? You may recognize this parameterization as that of a circle of radius a. As before, we're going to consider just the first quadrant, and we're going to note that the point a0 corresponds to the value that theta is equal to 0. The point 0a corresponds to the value when theta is equal to pi over 2. Using the idea that the area is equal to the integral from a to b of y dx, and noting that, as before, a and b are x limits, by quickly converting to y limits, we can say x for this region goes from 0 to a, and when x is 0, that corresponds to theta equals pi over 2. And when x is a, that corresponds to theta equals 0. So our area is equal to 4 times, because we're only taking the first quadrant, the integral from pi over 2 to 0 of y, which is a times the sine of theta, dx, which is negative a times the sine of theta d theta. Doing what we did before, we have area is equal to 4a squared times the integral from 0 to pi over 2 of the sine squared of theta d theta. Power reducing formula is going to give us 2a squared times the integral from 0 to pi over 2 of 1 minus the cosine of 2 theta d theta. And so a is equal to 2a squared times theta minus 1/2 times the sine of 2 theta evaluated from 0 to pi over 2. As before, the sign values are both 0, and when we plug pi over 2 in place of theta, we get that a is equal to pi lowercase a squared. So what happened? What does that mean? This proves the formula for the area of a circle. There it is. You've been told all your lives. A is pi r squared. Now you know why.